guys. Welcome back. We have attendance 1402. We don't have quiz today. We finished 10 quizzes. But we're going to have evaluation end of the class. I will give you time to do course evaluation. OK, don't forget to do attendance. I'm a little sick, sorry. I hope I don't make you sick. So let's see what we had before and what you're going to have today. OK, we are still in random process space. When a random variable changing in time. So with last week, we talked about some characteristic. Are you in? Are you guys listening? Yes. So we talked about some characteristic of random processes, mean, variance. In random process, we have two new characteristics. One is autocorrelation and one autocovariance. So similarity of the process to itself. So that's an interesting part for random processes. Last week, also we talked about a stationary random process. A stationary random process, we try to make the life easy because random process can be complex. That's why we have a version of that. We call that a stationary. So a stationary means statistics do not change over time. What is the statistics? Moments. Probabilistic moments, like variance, like mean, variance, skewness, or cortices, so different degrees, different moments. And regarding to a stationary, we have different type of a stationary, of course, a strict sense and wide sense. The strict sense is very strict, of course. But wide sense stationary random process is more important for us. Most of the systems can be modeled using wide sense stationary. In wide sense stationary, just two moments are actually time invariant. Mean and variance. And also autocorrelation in wide sense stationary is just depend on time difference. So what that means, it means, so we need to know this stuff. Autocorrelation is Rx, T1, and T2. It's same as saying tau. Tau is T1 minus T2, or T2 minus T1. So tau is a lag, time difference. So autocorrelation is just depend on time difference. So this is also one of characteristic of wide sense stationary. Wide sense stationary happening a lot. It's many systems. What else we talked last time? We also talked about white noise. So in random process, as you can see, when you have a signal, because random process is kind of modeling a signal. So a signal is kind of modeling dependencies in time too, Any point in this signal is kind of related to the previous points. So this dependency exists. But in white noise, we are saying that this dependency not exists. It means in white noise, autocorrelation is 0 in actually all the points, but in just one point is not 0, and that point is when tau is 0. So autocorrelation, so that's for white noise. Let me clean this up. So for white noise, we said white noise, mean is 0 in white noise. That's a characteristic of that. And autocorrelation, this is tau, is sigma square delta direct function of tau. That's a tau. So delta direct function is everywhere 0, but in tau is equal to 0 is infinity. So anyway, that's a mathematical way because we are in continuous space. Anytime we say process, we are kind of in continuous space. When we say sequence, it's become actually discrete. We're going to see sequences too today. Yeah, I think that was pretty much what we covered last time. But what we're going to cover today, we're going to go for dependency today. Dependency is hardest part in computer science, electrical engineering, in life. Relationship is, dependency is very complex things. And modeling dependency is hard, especially if dependency is to so many other parts. Right now, we are talking about dependency on time, but dependency can be to so many other things, and modeling dependency is one of the hardest things in computer science because it's coming from so many things, But we want to just consider simplest type of dependency. We just say, OK, dependency of a state or x, imagine it just depends on the previous state, not older, not more, just one step before. Can we do that? Yes, some simple models, they're just depend on previous, like weather, for example. Most of the time, weather now, it depends on weather like 2 minutes before, or 1 hour before, 1 day before. We're not going too much back. Or, for example, position of the robot is depend on previous position. Or multiple previous positions. The interesting part is that you can summarize multiple previous positions in different size of a state. Instead of having just x as a state, you can have x and x dot, mean velocity, or x2 dots, acceleration, or x3 dots, jerk. Still you stay depend on one step before, but you expanded a state. That's very, very important things. I hope you got that. But if you're not, don't worry. We're going to talk about that more. That's something very interesting, how you just depend on one step before, but kind of depend to many other times as well. In dynamic, we always depend on a couple of steps before because we want to see what is the velocity, what is the acceleration, what is the jerk, and so forth. OK? So that's what we want to start today. It's something very interesting because we are talking about dependency. We want to see how we can model dependency. It's just in time, simplest way, but it still is a start of something very interesting. So that's what we're going to talk today. The first dependency that we're going to talk is coming with this random walk. But we started last class. The random walk actually, the first time introduced by Paul, oh no, not Paul. Who was that? Carl, sorry. Carl Pearson in 95. And he just he asked actually himself if somebody just walk and take steps randomly, where will end up. So that picture showing like somebody drunk, for example, just walking around with different directions randomly, like different direction means this is steps. These steps are limited, you know. Limited is not go to jump infinite. So it's just jump, and we want to see what is the end. Some systems are like that. So we also can see this type of movements or this type of motion in the nature as well. So Brownian motion is one of them. The Brownian motion, we had that before. So a Brownian motion is like a continuous form of random walk. We're going to see that soon. So random walk means any state. First of all, this is a discrete process. So we can call it sequence. Sequence. So anytime we want to talk about discrete process, we call it sequence, because it's a sequence. It's numbers, multiple, like a vector of numbers. Anyway, so in this case, in random walk, the new state k is equal to previous state plus white noise. That's the white noise. We already know what is white noise. White noise is a type of process that is not correlated. But again, I'm going to explain that. So any signal kind of depends on previous state. Look at that. But the only signal, the only process that is not depend on previous state is like this. And this is called white noise. And this white noise doesn't have correlation. Autocorrelation, as I mentioned, is sigma square direct delta tau. So it means is always zero. Autocorrelation. There is no correlation. The only correlation is when these two points are just 1 point. In that case, the correlation going to sigma square. And this sigma square kind of specify this bandwidth, how this noise jumping around. Okay, so that's just general idea about random walk. So random walk coming from previous state and some random noise, something like that, white noise. So you can guess that this random walk is very simple type of dependency because it's just depend on previous state. Anywhere you were before, you just take a random step and you see where you go, and take multiple of them and find destination, something like that. What properties? First of all, is that memory or memoryless? It has some memory. The memory is a previous state. So we just have one memory. It's not memoryless. It has memory. Just depend one step past. So its memory, it has memory. Okay, one is that. What about dependency? Is it independent? No, it's dependent. Dependent are over time. It depends just to the previous state, but over time, I don't know why I wrote not independent over time. So I just want to say, yeah, yeah, anyway, this is just dependent on the previous state. Is not independent. Oh, yeah, I said it's not independent. It means independent, sorry. So why I wrote that? So it's not independent. It means dependent. It depends on the previous state. I'm sick, sorry. And a variance growing with time. Why variance growing in time? How you can see that in that formula. How that formula showing the variance growing in time. This formula is like a recursive formula. You're saying x5 is equal to, for example, x1 plus wk x. Okay, so maybe I write it like that. Is x4 plus wk, and instead of x4, you put x3 plus wk plus another wk. And instead of x3, put x2 plus wk plus wk plus wk. As you can see, we are accumulating wk's. You're adding them together. When this is like a recursive, and you are adding those variances. You're adding those variances. It means uncertainty growing in every step. So if here you have this much dependency, here you have more, here you have more. You know, it's get more and more and more. So that's another property. So the increase over time. So many phenomenon that we are dealing with right now, like a stock market, for example, in a simplified model of that, of course. Robot position is like that. And drifting in sensing, you know, when you are sensing and just, for example, in robotic, drifting happening a lot. When you just deal with one sensor, not fuse multiple sensors, you're just adding noise together. At the end, you are in some place that is not really supposed to be. You were thinking you are in X and Y, for example, but you are in X plus very big noise. That's called drifting. Drifting is like that. Because you are adding noises in each step, and finally you are in a position that's not supposed to be. That's called drifting. Drifting is a kind of random walk noise. Let's do one iClicker. Oh, I hope this is that I need to. You read that. I'm gonna go and active iClicker because I restarted my computer. I need little. Yes, so we want to see how we can move from discrete form to continuous. So what we need to do? You think about it, I'm gonna active that. Okay. That's good. Start the class. Cool. Okay, now it's active. So you can respond this one. So I'm just going to explain a little bit. So we want to see, okay, imagine in this random walk, we want to make that continuous. This is random walk. Okay, how make that continuous? These steps is delta t. These steps are delta t. How we can make this continuous? Continuous means make it a smoother, like that. So probably you need to do something for that. Do we need to increase the step size? Do we need to decrease a step size? Or find the limit of that to the 0? and scale the noise property. We can talk about noise property too, and remove the noise term. Because we have some problem with noise. Because noise going to infinity, we need to kind of, if we go to the 0, if delta t go to the 0, noise going to infinity. So we need to kind of control that. How? Let's see. Keep time discrete, but smooth the signal. I don't know. Which one is your answer? Let's see. I'm seeing most of you guys. Yeah, I see a normal distribution in your response, but they are around B, and that's correct. The B is the correct answer. Why? Because we need to make, anytime we want to make something continuous, we need to bring the delta t to the 0. You know, you need to find the limit of that to the 0, because when you make that small, but there is another part here, and this is scaling the noise. Scaling the noise is important because if you don't scale the noise, when you are adding infinite things together, when we make delta t smaller, it means you have unlimited, like infinite values, infinite noises, and we are adding them together. Infinite noise is going to be infinity, you know. And we need to scale that. So we can scale that by time. So this scale coming from that. So that's the correct answer. So scaling the noise coming from that, and delta t going to the 0. So normally scaling is coming from this. We can consider WK like a normal distribution, for example, from 0 and sigma square delta t. So this is a scale that we need. Scale the noise. In this case, if we scale the noise, we can find the continuous form. And the continuous form called Wiener process. I also wrote the name here. So it means continuous form of random walk is a Wiener process, or a Brownian process that we already saw before. OK. Thank you for that. That was good. Let's close this. Any question about this? Why B is correct? OK, so delta t going to the 0. We are make the steps smaller and smaller. It become continuous, of course. And scale the noise is because if you don't, we're going to go to infinity. We know it's going to add up to infinity because we are making the steps smaller and smaller, and the infinite steps becomes infinity, of course. OK, so let's go to Wiener process. So the Wiener process is a continuous form of random walk. So the Wiener process is actually, we already talked about Wiener process before, I think. Do you remember we talked about these pollen particles that actually Robert Brown discovered. Robert Brown in EE3180. He found with microscope and realized, oh, this pollen in top of the water, they're just jumping around. But he considered one of them, and here one of them is just moving randomly and make a path. But this is a continuous path, and he couldn't find a reason for that. Later on, I think 6 years later, 6 years, something, no. Yeah, no, like 80 years later, Albert Einstein found the reason for that. But anyway, the modeling happened later with Wiener, and that called Wiener process, that coming from Brownian motion. This is called Brownian motion, and later called Wiener process. Wiener process is a continuous form of actually random walk. Instead of taking random, movements in different direction with different steps in a discrete form. If we make it continuous, if the delta t going to the 0, we're going to get this motion. This is continuous, but very random, very random. It just depends on the previous steps. So to have actually to measure this motion properly, we need to have a initial point. The initial point is here. We consider that this Wiener process is, we call that this WT. Don't mistake the WT with white noise, okay? This is Wiener process, okay? This is Wiener process. However, it has some dependencies with white noise, of course, but so the Wiener process in point 0 is 0. This is initial step. Because you need to consider one initial. As you can see, that starts, for example, from 0, 0, the point 2 dimension here. OK, anyway, this is one. The initial step is 0. Wiener process in point 0 is always 0. And it has independent increment. The incrementing is independent. So it means incrementing going from a normal distribution around the mean, around the 0, with variance of this. And this tau is the scale that I mentioned. We need some scale here. Other than that, it's going to go to infinity. We need that scale tau. OK? So same as delta t that we had before in discrete form. Here we have tau in continuous form. How we can find it? We can show how we get from this. OK, so this is called Wiener process. So Wiener process is actually a process that has independent increment. Independent increment, like a little later minus WT, if you make this difference, is always random. It's always random. And this randomness coming from the normal distribution. Normal distribution with the mean 0 and variance sigma square tau. That's the tau. Tau is a lag. Remember, lag. The tau is lag. And lag is T1 minus T2 or T2 minus T1. The difference between these two. How we can obtain this from random walk? As I mentioned, random walk is a discrete form of that. So you just need to, this is random walk. So we need to get delta t going to the 0, same as the question that we had last slide. But what is k here? So to see what is k here, we need to see what is t. T is 0. We want to find relationship between k and t. So this is how we do changing from discrete to continuous. T is 0, delta t, 2 delta t, and k delta t. These numbers consider k. K is 0, k is 1, k is 2, and k is k, the end. So it means for t at the point k, for example, this time is k delta t. OK? So it means k is t over delta t. We just remove this k. So this relationship between k and t coming from here. Why we need that? Because we want to get the limit when delta t going to the 0. We want to see what's happening to that formula. We want to see what's happening to this formula. If we play a little bit with this formula, so we can write this when we change it to the t, it's going to be x t plus delta t equal to x t, this is delta t, delta t, okay, plus wk. And wk is a normal distribution, 0 and sigma squared delta t. Okay, to make the longest story short, after, so we bring this side, and this becomes d of x, because it's changing, it becomes d of x. And this wk is sum. This is sum, actually, because we are adding them. We show that that's why it's going to infinity if we don't scale it, because we add them multiple times. And d of, and if we write this as a d, change of this to this also going to be change of a continuous form of this. We call that omega, like omega t. And if we get integral, this is t. If we get integral, we're going to get xt is equal to wt plus a constant. And this constant is going to be 0 because this initial state is 0. So this x is actually Wiener process. Wiener process. So I wanted to just show if we go from discrete space in random walk, we're going to get these properties that we call it Wiener process. So it's obvious, as you can see in that picture, to when you make the steps smaller, you can normally get that property. However, in that property, that's a normal distribution. So that's why here we need to consider this is normal. In random walk, it's not always normal. In random walk, it is not always normal. Here we consider that normal, okay? Okay, so that was Wiener process story. The shape of that is something like that. And you can see in that motion as well. Here, however, we have pixels, so this is a little, again, discrete, but here is more continuous form. As you can see, it's just moving around. You can see these things in price of, the stock market, the oil, for example, going up, down. Right now is moving around a lot. Okay, that was the story behind random walk and Brownian motion and Wiener process. These stories help you to kind of remember things, That's why I try to tell the story behind them. But the next story that we're going to learn is about Markov. Markov is very famous. He is actually a Russian mathematician, Andrew Markov. Markov 9006. And he actually wanted to see if the dependency exists, how we can model dependency. Before him, most of mathematicians believe that probability theory is just working for independent events. So they were thinking if we make it dependent, it becomes too complex to model it. And it is really, it's so complex. So Markov decided to see if there is dependency, but very little dependency, just one step before, how we can model that. This is also called Markov property. Markov property is saying that in this formula, you can see this Markov property. So it's saying probability of some state like x, t plus 1, given previous steps like xt, t minus 1, t minus 2, t minus n, is just equal to probability of xt plus 1 given xt. It is all of the rest of information are garbage. Just like put them in garbage. I don't use them. To making decision now, this is the decision now. Xt plus 1. A state in xt plus 1 is just depend on previous step, just one step before, not before that. That is Markov property. So interesting part about Markov is he didn't use physics or engineering to actually prove that. He used literature. He actually studied some Russian poems, and he realized there is some relationship between these letters in terms of vowels and the sound of those. And he realized, oh my God, they are very related. If there is a poem, these alphabets or these characters are depend on each other. You can understand it because it's supposed to be smooth. When you are saying poem, they need to make a wave. And this came to his mind that this relationship can be modeled as a formula like that. And this is actually basic of so many other things, including large language models. So large language models working based on Markov model. You're saying the next character is dependent on previous characters. So large language models working like that. However, when you train them a lot and a lot and a lot, it becomes so real. You are thinking, oh, this is intelligent. It's not. It's just language model. So it's just predicting next characters and going and going and going. As far as it's bigger, as far as the data set is bigger, as far as the layers of system is bigger, you can predict more and more and more. That's why in language models you always have limitation. That's why in language models always, when you are asking something, you need to be careful, okay? It's not always true. Sometimes it's just based on information that they trained based off those and just find the next characters, next words, next sentence, and make something amazing. So that's the basic. The basic of that is coming from Markov process, of course. So the Markov process is this. The future is independent of the past, given the present. You don't need to live in past. Just live now, and you can, based on now, you can make one decision further. Interpretation, knowing the current state gives all necessary information. That's a very good explanation. You have all information for predicting the future. I told you, we want to predict. That's the reason of modeling. When we model the system, we want to predict. And the simplest way to predict is just predict future based on, information that you have now. This is the simplest prediction. The process forgets its history. That's another explanation for Markov process. Anyway, this is Markov's story. You're going to see Markov a lot later. Why Wiener process is Markov? So Wiener process this is Wiener process, W-T. So you can write Wiener process. Okay, first of all, anytime I ask you to prove something is Markov or not, you need to show this formula. You need to show the future is always coming from the present and some independent noise. because it's a still process, so you need to have some white noise adding to these things to make it process. So anytime you want to prove something is Markov, you need to show this characteristic. Future is equal to the present plus some independent noise, because this independency is important, because dependency is just between these two. This is independent. It is just make it a process. That independent noise is the reason to make it a process. But dependency is just between these two, just one-step dependency. Okay? So how we show for Wiener process, we always can write this, because these two are going to cancel out each other, so we can write it like that. And in Wiener process, we know that the difference between two Wiener process, t and t plus tau, a little bit later, is independent and is Gaussian. So we kind of proved that the future, this is future, is past plus some Gaussian independent noise. Gaussian independent noise. That's the definition of Wiener process. In Wiener process, difference between two consequent process, 2 points after each other, is always Gaussian independent. Gaussian white noise. So we proved that this formula exists. So the key idea, and then we can write that. We can say probability of Wiener process t plus tau, given all the past, is equal to probability of the Wiener process t plus tau, given Wiener process at t, not before t. We just removed past to present. This is just present. This is present. This is future. We are estimating future. We are predicting future based on present. Wow, that's interesting. And the conclusion, Wiener process satisfies the Markov property, and it is okay. So I'm not going to